Hello, I am Michael Tonks from the University of Florida, and today I'll be talking about our work on the development of a multi-scale corrosion model for valve steels in a gasoline engine environment. Now, this is work with various collaborators. So we have various collaborators at the University of Florida, University of Wisconsin-Madison, Idaho National Lab, and TENNECO. I'm the PI on the project, but the people who are doing the work are our students and postdocs, and I'm showing them here in orange. Now, this work is being funded by the Department of Energy in the Advanced Vehicle Technologies program. Now, with gasoline engines, we're always trying to drive engines to higher and higher temperatures, and that's because it helps efficiency of the engine and also improves emissions. However, as we drive to higher and higher temperatures, we can start to have issues with our materials. And one specific example of this is when you get to higher temperatures, you can start to activate your valve materials to corrosion in the engine environment, so in the combustion chamber. And so you can start to get very significant corrosion, which has a large impact on the performance of the engine. And so we have to replace the engine valves. Now, the way that most companies deal with determining what material to use for the valves is they just have effectively a database or something like this table that I'm showing here, where for each material, there's some max temperature where they've certified that material. And if they change to an engine design that has a higher temperature, then they have to use a different material. And that can be often a totally different category of material, which can be a lot more expensive. Now, the goal of this project is to develop a tool to help us take an existing alloy and try to optimize and improve its performance without having to move to a whole new category of materials. And we're specifically targeting valve steels, so the 21-2N and the 23-8N valve steels, and looking at how we might be able to improve these steels. And so these are stainless steels, so we have a high level of chrome, and then we've got some manganese and some nickel. Now, the tool that we're developing is called the Stainless Steel Alloy Corrosion tool, or the SStAC tool. And the goal is to develop a tool that can be used to optimize these engine alloys, these valve alloys. And so it has to be able to predict the corrosion as a function of the alloy composition, and also as a function of the microstructure of the valves. And in order to develop this capability, we are involving experiments, both lab experiments and also engine tests for validation. And we're also using lower length scale modeling. So we're using phase field models and also density functional theory. Now, once completed, our tool, our SStAC tool, will be an open source tool, and it will be a finite element based tool. So we're developing it using the finite element method and based on an existing finite element library called MOOSE. So this is an open source library where MOOSE stands for the Multiphysics Object-Oriented Simulation Environment. And our tool will be able to predict the geometry of a specific engine valve and predict the corrosion in both 1D, 2D, and 3D. And so we'll be able to dictate the composition of the gas, the temperature history, but also the composition of the alloy and some microstructure descriptors like the average grain size or second phase particle composition or concentrations. And so with that, we'll be able to predict the corrosion of the engine valve. And the way that we actually are going to resolve the formation of the oxide layer within our SStAC tool is using the extended finite element method. So here's just a simple example of this, where we're having growth in 1D. And so we can actually have this alloy, this oxide layer grow using the capabilities of XFEM. Now, as we develop our model, we need to have this sensitivity to microstructure and to alloying elements. And so we're using a multi-scale approach with both experiments and modeling to allow us to do that. So at the University of Wisconsin-Madison, they're focusing on the development of the SStAC tool itself and also on carrying out the engine tests. At the University of Florida, we are trying to provide the real lower length scale information about microstructure and alloy composition using phase field simulations, where we're developing a new capability also using MOOSE, and also density functional theory calculations in order to get important properties that we may not know. And then Idaho National Lab is helping us with using the Moose framework. And then TENNECO is supplying the engine valves and also carrying out engine testing to help us with validation. Now I want to start by talking about our laboratory experiments, because we're allowing the experimental results to really dictate how we develop the model, and I'll illustrate that as we move forward. So we take engine valves supplied by TENNECO, and then we section out samples from the valves, and we characterize their microstructure, and we also characterize second phase particles and so on, also the texture. And then we take those samples and we put them into an experimental apparatus that we've established at the University of Wisconsin-Madison, which has a furnace that allows us to control the gas environment within the furnace. And then we can use the furnace and go through different temperature ranges and temperature cycling and so on, and then look at the corrosion of our samples. So we then remove the samples, and then we can do microscopy and characterization of the samples after oxidation. Now, our preliminary results, we've completed testing all the way up to 1,000 hours on two different alloys, the 21-2N and the 23-8N alloys. And what we found to begin with is that the 23-8N, we see a lot more scatter in the results when we do multiple samples, and we're seeing just more oxidation in general. In addition, with the 21-2N, we're seeing much less oxidation and much less scatter. Now we can look at EDS results on results from 275 hours to give us some idea of what's going on here. And what we see is that within the 21-2N, we have a lot more manganese. And so we're getting this manganese oxide layer that's forming, which seems to be more protective, which we don't see in the 23-8N. So the manganese seems to be important. So we're going to look into that in more detail now. So we've just focusing on the 21-2N with the larger manganese now. We've done SEM on samples from various amounts of oxidation time. And one thing that stands out is we see the oxide layers forming, but we also see the formation of voids. And the voids are forming at the metal oxide interface. So this seems to imply that we have metal ions that are actually leaving the metal, transporting through the oxide, and then reacting with the oxygen, and that's what's causing the formation of, or the growth of the oxide layer. Also, we've done STEM EDS line traces on these samples, and it starts to give us a very good idea of what are the compositions of the oxides that are forming. And it's an interesting, we see some interesting behavior. So right on the surface at the very beginning, so this is 50 hours, we see the manganese oxide layer form, and we have a fairly large, the large oxide layer. But then we have a thinner oxide layer that seems to have manganese and chrome. So there's a manganese chrome oxide spinel that's forming. Now, as we go on to longer time, we still have the manganese oxide, but now that spinel is starting to be much larger than the manganese oxide. And that continues on. We also start to see the formation of a chrome oxide, and it's most evident here. So we have the manganese oxide, and then we have a depletion of manganese. So we just have chrome and oxygen. So we have a chrome oxide layer, then we have the spinel layer, and then we have the metal. And now this sample is just sort of done in reverse here at the 1,000 hours. This is our free surface, but we see the same general behavior. So we can go through and actually look at the oxide thickness of the oxides over time. So at 50 hours, our manganese oxide is our largest oxide, but from then on, it's essentially shrinking, and we're getting less and less manganese oxide. Now, at the same time, we have a chrome oxide layer that forms and starts to grow, though it's never very large. But what really is dominating the oxide growth is the growth of this spinel. Now, if we look at this in more detail with thermodynamics, we can start to understand what's going on here. So if we look at the oxygen partial pressures of these different oxide types of oxide, manganese, chrome oxide, and the spinel, the most stable oxide is going to, thermodynamically, is going to be the spinel, and then the chrome oxide, and then the manganese oxides, and there's various types, are going to be less stable. And that explains why over time we see the manganese oxide thin and the chrome and the spinel to grow. But a valid question then is, well, why, if the manganese oxide is less stable, then why did it form in the first place? And one possible reason for that could be kinetics. So it could be that the manganese is able to migrate easier and start to form this oxide layer. So we started to look at this more now with density functional theory. So with DFT, we've looked at the vacancy formation energy for different types of vacancies. In the metal, some representative alloy, and then the spinel and the manganese oxide. And one thing that stands out right away is that the vacancy formation energy of the manganese is quite low, while the oxygen vacancies would be much higher, and the oxygen vacancies are also higher in the spinel, though the metal vacancies also have a fairly large formation energy. So this very low vacancy formation energy implies that we'd have a fair number of vacancies in the spinel, and that may be why the manganese can migrate more readily there, and so we get this faster formation of the manganese oxide at the very beginning of its life. Now we're using DFT to look more into now the migration barriers to give us even more information about that. We've just begun this work, so we're looking at the spinel first, and we've started with the manganese. And so we're looking at different ways that manganese can move through the material, and we can get migration barriers from that, but that work is still in progress. Now we are developing our phase field model, which is going to allow us to look at the actual growth of the oxides and to actually spatially resolve the evolution of the oxides over time. And the way that we do that is we represent various aspects of the microstructure with variable fields that evolve and change over time. So within our domain, anywhere where this variable psi1 is equal to 1 will be an alloy. And anywhere psi2 is equal to 1 will be the spinel, psi3 is equal to 1 will be the chrome oxide, and so on. And so we have 6 variables representing all the different types of regions of the material that we might have. So we have our 4 phases, and also we have a void phase, and then we have the gas phase where we have the free surface. And so we have 6 variables representing the evolution of those. We also have 4 additional variables describing the molar volumes of chrome, manganese, oxygen, and vacancies. And then the evolution of these variables are defined by partial differential equations that are functions of derivatives of our overall free energy of our system. So it's trying to lower the free energy over time. And so we define the free energy as a function of all of these variables. So we have a chemical part of the free energy, and we're taking that information from thermodynamic databases and making some approximations. So we can have a free energy curve for each phase. And then we also need to include the electric energy. So we need to have the impact of the electric potential, because this is an electrochemical problem. And then finally, we will eventually add a mechanical energy as well due to mismatched strains that can form in the material. So we've implemented our model with, so far without the chrome oxide phase and without the mechanical energy, but with the electric energy. And we've started some preliminary investigations just in 1D is what I'm showing here, though we've done more than that. But I want to demonstrate some of the capabilities. So currently we're assuming all the different compositions are moving with the same kinetic rates until we get a better idea about the kinetics from the DFT. But we can look at just the impact of boundary conditions. So we have an initial microstructure where we have some metal, then we have a void, and then we have some more metal, and then we've got a thin spinel, a thin manganese oxide layer, and then our gas, where our oxide will grow into the gas region. And we're setting boundary conditions. So on the left, we're allowing manganese and chrome to enter the system. And on the right, we're allowing oxygen to enter the system. And we're defining that in terms of a set chemical potential on the boundaries. And when we set the chemical potential of all manganese, chrome, and oxygen to be equal, then first off, the void grows and actually overtakes this secondary metal phase. And so we end up just having a void in between, right on the oxide metal interface, which is what we've seen in the experiments. And then when the chemical potentials are all equal, both the manganese oxide and the spinel phase grow at equal rates. When we have a higher chrome potential, so we have more chrome entering the system, then the spinel grows faster because there's more chrome. When we have more manganese entering the system, then the manganese oxide grows faster. However, when we have more oxygen in the system, the spinel also grows faster, and that's because the spinel is better able to accommodate oxygen than the manganese oxide. And so that could be another reason why we're seeing the faster spinel growth in addition to just thermodynamics, is if there's more oxygen available in the system. So all of this, the experiments, the density functional theory, and the phase field are all going in to try to add our critical capabilities to the STAC tool. And the most important part of the STAC tool will be a corrosion model at the macro scale. So we're working on developing that corrosion model as well. But this is a macro scale model, so we need to make assumptions. So first off, we're just going to have a single representative oxide. We also need to have other assumptions. So we're assuming defect fluxes are constant in the oxide. We're assuming the interfacial reactions are at equilibrium and a zero net charge in the oxide. So we have a charge compensation condition. And then we have calibrated parameters that we set by comparing to experiments. And then we have the oxygen vacancy migration energy. We may eventually replace that with DFT results. And then we're also fitting the electron untrapping energy. So we've done initial fitting of our model by comparing to experimental data from the literature for a stainless steel alloy without manganese. And then we compare the corrosion rate, and we get reasonable comparison within 25% error, which is the pink lines, with the 23.8N results that have the small amount of manganese. But we are not getting good comparison with the 21.2N, which has a lot more manganese. So this again shows us the importance of manganese. And so we're now continuing to move forward, and we'll improve our corrosion model by carrying out more experiments and also using the lower length scale simulation results to provide the information to make that our model now more sensitive to alloying elements. So to conclude, we're working on developing the STAC tool. This will be an open source tool that will be able to predict the corrosion of engine valves, and it will include the effect of alloying elements and microstructure. And we're using a multi-scale approach to develop that with experiments and lower length scale modeling. And so far, we've been able to show the critical impact of manganese on the corrosion of these valve steels, and how the manganese chrome oxide spinel seems to be the most stable oxide. And we've started out with a preliminary fit for our macroscale corrosion model, but we're now working to improve that fit using additional experiments and also our lower length scale simulation results. And with that, I can take any questions. And you can just enter your questions and I'll answer them through the dialogue.